Welcome to Don't Forget to Subscribe. Imagine standing at the base of a structure so immense that its peak is literally piercing the clouds, disappearing into a realm where the air is thinner and the temperature is notably cooler than the desert floor beneath your boots. You are looking at the Burj Khalifa, a silver needle of glass and steel that pushes the very limits of what human beings can achieve on this planet. This isn't just a building, it is a declaration of existence carved into the skyline of Dubai. Right now, as you stand at the ground level, the sun has just dipped below the horizon, plunging the streets into twilight. But if you were to sprint to the elevators and ascend to the observation deck at a speed of 10 meters per second, you would witness a miracle of physics: the sun would rise again. You can literally watch the sunset twice in a single evening, a phenomenon usually reserved for pilots or astronauts. This vertical city stands at a staggering 828 meters or 2,717 feet. To put that into perspective, if you stacked 3 Eiffel Towers on top of one another, you would still be looking up at the Burj Khalifa spire. It is twice the height of the Empire State Building and nearly 200 meters taller than its closest rival at the time of its completion. But height is only the surface of this story. Beyond the glitz and the world records lies a hidden engineering secret that almost brought the entire project to a standstill, a revelation about how the building actually breathes and moves to survive the violent forces of the atmosphere that we will uncover later in this journey. The sheer scale of the Burj Khalifa defies standard architectural logic. It weighs approximately 500,000 tons when empty. That is equivalent to the weight of 100,000 adult African elephants, all concentrated on a single patch of desert sand. The amount of concrete used in its construction is equally mind-boggling: 330,000 cubic meters. If you took that concrete and laid it out in a sidewalk, it would stretch for 1,900 kilometers, or roughly the distance from London to Rome. The external cladding is a shimmering skin made of 26,000 hand-cut glass panels, covering an area equivalent to 17 football pitches. It takes a specialized crew of window cleaners nearly 4 months just to wash the entire exterior once from top to bottom. By the time they finish the last window, it is already time to start again at the peak. This project was never intended to be just another skyscraper. It was a strategic gamble by the ruler of Dubai, Sheikh Mohammed bin Rashid Al Maktoum. In the early 2000s, Dubai recognized a terrifying reality. Their oil reserves, the very lifeblood of their rapid modernization, were finite. They needed a new identity. They needed to pivot from an oil-dependent trade hub to a global destination for tourism, finance, and luxury real estate. The Burj Khalifa was designed to be the centerpiece of downtown Dubai, a beacon that would draw the eyes of the world and prove that the impossible was merely a starting point. However, building the world's tallest structure in the middle of a shifting desert landscape was an invitation to disaster. Most people assume that if you have enough money and enough steel, you can build as high as you want. That is a dangerous misconception. At these heights, the wind isn't just a breeze, it becomes a physical sledgehammer. The higher you go, the more the wind behaves like an ocean current, swirling around the edges of the building and creating low-pressure zones that can literally shake a skyscraper to pieces. Engineers call this vortex shedding, and for a building of this height, it could be fatal. The Burj Khalifa had to be more than strong, it had to be smart, it had to be aerodynamic in a way that no building had ever been before. This wasn't just a construction site, it was a laboratory where the rules of gravity and fluid dynamics were being rewritten in real time. The stakes were absolute. A single miscalculation in the foundation or a failure to account for the thermal expansion of the steel could result in a structural failure that would be visible from space. When the project broke ground in 2004, the skeptics were vocal. They pointed to the unstable nature of the Gulf's geology, a layer of carbonate cloudstone and weak sand that seemed incapable of supporting such a monstrous load. They questioned the logistics of pumping liquid concrete nearly a kilometer into the sky before it hardened in the 50 degrees Celsius heat. Yet, the vision moved forward. The client, Emaar Properties, demanded a record breaker, and they hired the architectural firm Skidmore, Owings & Merrill to deliver it. The lead architect, Adrian Smith, and structural engineer Bill Baker knew they couldn't just scale up a traditional square building. They needed a radical new shape. They looked to the hymenocallis, a desert flower with long petals radiating from its center, for inspiration. This led to the buttressed core design, a hexagonal central hub supported by 3 wings. This shape isn't just aesthetic. It provides the ultimate structural stability while maximizing the views for the residential and office spaces. But even with this revolutionary design, the team faced a terrifying realization during the initial wind tunnel tests. The original design might not be enough to stop the building from swaying several meters at the top, which would make the occupants physically ill. This forced a massive, last-minute redesign of the building's orientation, a decision that saved the project but pushed the engineering team to their breaking point.
This is the story of how 12,000 workers, thousands of tons of high-strength concrete and a vision of pure ambition combined to create a vertical desert oasis that redefined the limits of the human species. To understand how the Burj Khalifa stays upright, you have to look past the shimmering glass and dig 50 meters deep into the shifting sands of the Arabian desert. The first and perhaps most terrifying engineering challenge was the foundation. In most places, when you build a skyscraper, you dig until you hit solid bedrock, but in Dubai, there is no bedrock in the traditional sense. Beneath the surface lies a weak, porous mixture of sandstone and siltstone saturated with corrosive groundwater. It's essentially building a mountain on a layer of wet crackers. To prevent the 500,000-ton structure from simply sinking into the earth, engineers had to rely on a principle called skin friction. They didn't just rest the building on the ground, they pinned it into the earth using 192 massive reinforced concrete piles. Each pile is 1.5 meters in diameter, about the width of a standard dining table, and plunges 50 meters into the ground. These piles don't sit on a solid base. Instead, the friction of the soil pressing against the sides of the concrete cylinders is what holds the building up. It is the same principle that keeps a nail tight in a piece of wood. The total weight of the concrete in this foundation mat alone is 45,000 tons, which is roughly equivalent to the weight of a heavy cruiser warship. If even one section of this foundation had settled faster than the others, the entire tower would have begun to lean, creating a leaning tower of Dubai that would have been a global catastrophe. The second enemy was the sky itself. At 828 meters, the Burj Khalifa isn't just a building, it's a lightning rod and a massive sail. The most dangerous force at this altitude is something called vortex shedding. When wind hits a flat rectangular building, it creates swirling eddies of air on the opposite side. These vortices alternate from side to side, creating a rhythmic push-pull effect. If the frequency of these wind gusts matches the natural vibration frequency of the building, the structure can begin to sway violently, eventually leading to a structural failure, like a paperclip being bent back and forth until it snaps. To solve this, the engineers didn't try to build a wall against the wind, they decided to confuse it. This is why the Burj Khalifa has its iconic stepping design. As the building rises, each of its 3 wings retreats inward at different heights. This means that at every level of the tower, the wind encounters a different shape. The vortices can never synchronize because the building's profile is constantly changing. It breaks the wind's rhythm before it can even start. During the design phase, the team conducted over 40 intensive wind tunnel tests, simulating once-in-a-century storms to ensure that even at the very top, the sway would be almost imperceptible to the human inner ear. Then there was the problem of the load-bearing structure and the materials themselves. To reach these heights, the team utilized a buttressed core system. Imagine a central hexagonal hub of high-strength concrete, reinforced by 3 outer wings that act like the flying buttresses of a Gothic cathedral. This design provides immense lateral stiffness, preventing the tower from twisting or bending under the massive seismic loads that can occur during rare but possible regional earthquakes. But how do you get liquid concrete 600 meters into the air before it sets? This was a feat of logistics that had never been attempted. They used 3 of the world's most powerful high-pressure pumps, forcing the concrete up a single pipeline. The pressure required was nearly 350 bar, roughly the same pressure you would experience 3,500 meters under the ocean. Because the Dubai heat can reach 50 degrees Celsius, they couldn't pour during a day. The concrete would have dried instantly, cracking and losing its yield strength. Instead, they mixed the concrete with 3,000 tons of ice every night, pouring only under the cover of darkness to ensure the chemical reaction happened slowly and perfectly. Finally, the engineers had to account for thermal expansion. In the scorching sun, the Burj Khalifa actually grows. The side of the building facing the sun expands as the steel and concrete heat up, while the shaded side stays cool. This creates a banana effect, where the building slightly bows away from the sun. The glass cladding had to be designed with special joints that could slide and shift as the building breathed. We are talking about a safety factor that accounts for millimeters of movement across a structure nearly a kilometer tall. Every single joint, every bolt, and every pane of glass had to be a masterpiece of precision. If the seismic load calculations were off by even a fraction of a percent, or if the load capacity of the central core was overestimated, the sheer gravity of the building would have crushed its own base. This wasn't just construction, it was a high-stakes battle against the fundamental laws of physics, where the margin for error was zero. The construction of the Burj Khalifa began in January 2004, marking the start of a 6-year marathon that would push human endurance and mechanical limits to the breaking point. At the peak of construction, the site was a vertical city in itself, populated by a staggering workforce of 12,000 people every single day. These individuals represented over 100 different nationalities, creating a modern-day Tower of Babel in the heart of the desert. But this wasn't an easy assignment. Working on the Burj meant battling the brutal climate of the United Arab Emirates. In the summer months, ground-level temperatures regularly soar above 50 degrees Celsius, which is roughly 122 degrees Fahrenheit, hot enough to cause heat stroke in minutes. To keep the project moving, the work continued 24 hours a day in shifts. While the rest of Dubai slept, the construction site was a neon-lit hive of activity, with the sound of machinery echoing across the sand. The sheer logistical challenge of moving 12,000 people and thousands of tons of material up and down a structure that was growing by the day required the coordination of a military operation. The secret to the building's rapid ascent was a technology called automatic self-climbing formwork. Imagine a massive robotic steel mold that wraps around the building's concrete core. Once a section of concrete was poured and achieved its yield strength, hydraulic jacks would slowly lift this entire assembly, weighing hundreds of tons, up to the next level. It was a rhythmic mechanical dance that allowed the tower to grow by one entire floor every 3 to 4 days. To visualize that speed, imagine building a standard 2-story suburban home from the ground up in just a few hours, then repeating that feat over 160 times without a single day off. This relentless pace was necessary to meet the ambitious deadline set by Emaar Properties, but it placed an immense strain on the load-bearing structures and the men who monitored them. As the building climbed past the 500-meter mark, the engineers faced a problem that had never been solved on this scale: how to get the building's lifeblood, concrete, to the top. In November 2007, the team set a world record that still leaves engineers in awe. They used 3 high-pressure pumps to force liquid concrete to a vertical height of 601 meters. To understand the physics involved, imagine trying to blow thick syrup through a straw that is 6 football fields long, pointed straight at the sky. The pressure inside the pipes was nearly 350 bar, equivalent to the weight of a small car pressing down on every square inch of the pipe's interior. If a single joint had failed, the resulting explosion of concrete would have been as lethal as a cannon blast. The achievement wasn't just a record, it was a testament to the material science and the unconventional solutions the team had to invent on the fly. Hovering above it all were the 3 unsung heroes of the Burj Khalifa, the Fawel Favco cranes. These 3 massive Australian-made machines were the highest cranes ever operated. They were climbing cranes, meaning they didn't sit on the ground. Instead, they were anchored to the building's core. As the building rose, the cranes would use their own hydraulic systems to jump themselves up to higher floors, essentially pulling themselves up by their own bootstraps. The crane operators lived a life apart from the rest of the world, working in small cabs nearly a kilometer in the sky, where the wind speeds were significantly higher and the air was noticeably cooler. One mistake by a crane operator at that height, dropping a single steel beam, could have resulted in a catastrophic accident for the workers below.
But the story of the Burj Khalifa isn't just one of steel and records. It is also a story of human struggle and forgotten stories. In 2006, the project faced a massive crisis when over 2,500 workers, frustrated by low wages and poor living conditions in labor camps, staged a violent protest. They blocked roads and damaged construction equipment, highlighting the true cost in effort and the social friction inherent in such a massive undertaking.
This event forced a temporary halt to construction and remains a controversial chapter in the building's history. It serves as a reminder that behind every shimmering mega-project is a foundation of human labor that often goes unrecognized in the glossy brochures. Then came the year 2008, the moment the entire dream almost collapsed. The global financial crisis struck like a lightning bolt, and Dubai's real estate market, which had been the engine of the city's growth, ground to a halt. The Burj Dubai, as it was then called, was nearly finished, but the money had run out. The project faced the very real possibility of becoming the world's tallest white elephant, a half-finished skeleton in the sand. In a dramatic 11th-hour intervention, the ruler of Abu Dhabi, Sheikh Khalifa bin Zayed Al Nahyan, provided a $10 billion bailout to save Dubai's economy. To honor this gesture, at the grand opening ceremony on January 4, 2010, the building was officially renamed the Burj Khalifa. This naming wasn't just a formality, it was a symbol of the political and economic interdependence that allowed the project to cross the finish line. The final engineering miracle was the installation of the spire. This 4,000-ton structure of structural steel was too heavy and too high for any crane to lift. Instead, the engineers built the spire inside the top of the building, like a hidden core. Then, using a series of massive hydraulic jacks, they telescoped the spire upward from the 156th floor. It was a slow, agonizing process that took months, pushing the final point of the building to its record-breaking 828 meters. When the final bolt was tightened, the team had not only broken every record for height, but had also created a monument to human ambition that survived financial ruin, extreme weather, and the very limits of physics. When the Burj Khalifa finally opened its doors on January 4, 2010, the world watched in stunned silence as a 10-minute firework display erupted from the sides of the building, turning the entire tower into a pillar of flame and light. It wasn't just a party, it was the coronation of a new world champion. The Burj Khalifa didn't just break the record for the tallest building, it shattered it, standing 320 meters taller than the previous record holder, Taipei 101. To put that in perspective, the difference in height between the two is roughly the size of the Chrysler Building in New York. On that day, the Burj claimed no less than 7 world records, including the highest number of stories at 163, the highest occupied floor, and the elevator with the longest travel distance in the world. These elevators are masterpieces of vertical transportation, moving at speeds of 10 meters per second or 36 kilometers per hour. That is faster than most people can sprint, and yet the ride is so smooth that you can balance a coin on its edge during the ascent and it won't fall over. But beyond the records, the Burj Khalifa had to solve an invisible problem that plagues every super tall structure, the stack effect. Imagine a giant chimney. Because the air inside the building is cooler and denser than the scorching desert air outside, the building acts like a massive vacuum. This pressure difference can cause doors to slam shut with lethal force or create whistling winds in the hallways that sound like a haunting choir. To manage this, engineers designed a series of airtight lobbies and specialized ventilation systems that act like airlocks on a spacecraft. This is the building's respiratory system, and without it, the interior of the Burj Khalifa would be a chaotic wind tunnel. Furthermore, in a city where water is more precious than oil, the building's cooling system produces a staggering amount of condensation. Instead of letting this water go to waste, engineers created a collection system that harvests 15 million gallons of water from the air every year. That is enough to fill 20 Olympic-sized swimming pools annually, which is then used to irrigate the 27 acres of lush parkland and greenery surrounding the base of the tower. However, no project of this scale is without its shadows. For years, a persistent story circulated on the internet that the Burj Khalifa was not connected to a municipal sewage system and that a fleet of poop trucks had to haul away the waste every single day. While this made for a shocking headline, the reality is more nuanced.
While the building itself was designed with state-of-the-art plumbing, the city of Dubai's rapid expansion meant that the local sewage treatment plants were temporarily overwhelmed during the building's early years. This led to the sight of long queues of trucks waiting to dump waste at treatment facilities, a systemic failure of urban planning that stood in stark contrast to the high-tech elegance of the tower. It serves as a reminder that a megaproject is only as successful as the infrastructure that supports it. Additionally, the final price tag of $1.5 billion was a staggering sum, representing the cost of nearly 150 Boeing 737 airplanes. Critics argued that the building was a monument to vanity, an empty needle in the sand designed more for prestige than for actual necessity. Yet, a decade later, the legacy of the Burj Khalifa is undeniable. It transformed Dubai from a regional trade hub into a global must-see destination. It proved that a city could literally build its way into the future, using architecture as a form of soft power to attract investment and tourism. The engineering breakthroughs achieved here, from the buttressed core to the high-pressure concrete pumping, have become the blueprint for a new generation of megatolls, like the Jeddah Tower in Saudi Arabia or the proposed The Line in Neom. The Burj Khalifa shifted the center of gravity of the architectural world from the west to the east, proving that with enough capital and human ingenuity, the sky is no longer a limit, but a floor. Philosophically, the Burj Khalifa is a mirror of our collective human ambition. It represents our primal urge to reach upward, to conquer the elements, and to leave a mark that will last for centuries. It is a monument to the fact that we can build things that are larger than our fears and taller than our doubts. But it also stands as a warning that the higher we climb, the more we depend on the invisible systems and the thousands of forgotten hands that keep the structure standing. As we look to the future, we must ask ourselves, what is the true limit of our vertical ambition? Is there a point where a building becomes too tall for the earth to sustain? Or is the Burj Khalifa just the first step in our journey to the stars? Thank you for watching this deep dive into the limits of engineering. If you found this journey to the top of the world fascinating, don't forget to hit the like button and subscribe for more stories of human ambition and mechanical marvels. Now a question for the comments. If you had the chance, would you live on the 163rd floor, or does the idea of being nearly a kilometer in the air make your stomach turn? Let us know your thoughts below, and we'll see you in the next one.